In 1961, a scientist ran the same weather simulation twice. Same equations, same machine. He expected the exact same forecast. But the second run started from a number rounded ever so slightly, 3 decimals instead of 6. A difference smaller than a rounding error. It should have changed nothing. Instead, the two forecasts slowly drifted apart, then split completely into 2 entirely different weathers. That tiny rounding had rewritten the future. This is the butterfly effect, and it sets a hard limit on what we can ever predict. For centuries, science ran on a comforting promise. The universe is like clockwork. If you know exactly where everything is and how it's moving, the laws of physics grind forward and tell you the future. The mathematician Pierre-Simon Laplace put it boldly. A mind that knew the position and speed of every particle could see the entire future and the entire past in a single glance. Nothing would be uncertain. And for the tidy problems, it works. We predict eclipses centuries ahead, land probes on distant worlds. Determinism seemed to mean the future was, in principle, wide open to us. Then came Edward Lorenz. In 1961, he was running one of the first computer models of the weather, a dozen equations looping forward step by step. One day, he wanted to re-examine a run, so he restarted it partway through, typing in the numbers from a printout. But the printout showed only 3 decimal places, while the computer had been using 6. So instead of 0.506127, he entered 0.506. A change of about 1 part in 4,000. He expected the weather to repeat. He went for coffee. When he came back, the new run had drifted from the old one, gently at first, then violently, until the two weathers had nothing in common. The same equations had produced 2 wildly different futures. Lorenz had stumbled onto something profound. Later, the idea got its famous name from the title of a 1972 talk of his. Does the flap of a butterfly's wings in Brazil set off a tornado in Texas? The heart of it is a property called sensitive dependence on initial conditions. Start 2 copies of a system almost, but not exactly, alike, and the tiny gap between them grows. And it doesn't grow steadily. It grows exponentially, the distance between the 2 doubles and doubles again and again, until what began as a microscopic difference fills the whole picture. You can watch it with a double pendulum, one arm swinging from the end of another. Release 2 of them from almost the same angle, and for a second they move as one. Then they diverge, and within moments they are swinging in completely different directions, wild and unrepeatable, even though each obeys simple, exact laws of motion. 2 years later, Lorenz stripped the idea down to just 3 equations, a bare-bones model of convection. When he traced their solution through space, it drew this: 2 spiraling loops, like the wings of a butterfly. It's now called the Lorenz attractor. The path loops around one wing, then the other, never exactly repeating, never crossing itself, never settling down. Yet it always stays on the same delicate shape. And here is the crucial twist. There is no randomness in these equations at all. Feed in the exact same starting numbers, and you get the exact same path every single time. This is deterministic chaos. That's the paradox at the center of it. The system is perfectly determined by its laws, and yet, in practice, utterly unpredictable, because we can never know the starting point with infinite precision. Once you know the signature, you spot chaos everywhere. Smoke curling off a flame, a dripping tap that won't keep a steady rhythm, the swirl of turbulence, the long-term dance of planets and moons. But chaotic doesn't mean anything goes. The Lorenz path never flies off to infinity, it's forever trapped on its butterfly. Chaos is unpredictable in its details, yet bounded in its shape. That's why we can still say plenty about a chaotic system. We may not know exactly where it will be next week, but we often know the world it's confined to. Climate can be steady even when weather is not. Which brings us back to the sky. Every weather forecast starts from measurements, and measurements are never perfect. There's always a tiny error, a butterfly, hiding in the numbers. And chaos doubles that error, again and again. In the atmosphere, the gap roughly doubles every few days, so today's speck of uncertainty swells until it swallows the entire forecast. This sets a wall. Even with perfect equations, a flawless model, and every measurement we could dream of useful daily, weather prediction runs out at around 2 weeks. Past that, the butterflies win. So forecasters stopped chasing a single answer. Instead, they run the model many times, each nudged slightly differently, and watch the spread. Where the runs agree, we're confident. Where they scatter, the future is genuinely open. That spread is a big part of where a percentage chance of rain comes from. Chaos rewired how we think. It broke Laplace's dream in two. A system can be fully deterministic, ruled by exact laws with no dice at all, and still be impossible to predict for long. Determinism was never the same as predictability. The equations may know the future perfectly. We simply can never read our starting point sharply enough to follow along. So the butterfly isn't really about insects and tornadoes. It's about how the smallest unknown, amplified by nature's own arithmetic, can outrun our knowledge entirely. Between the clockwork we can predict and the randomness we can't lies a third world, perfectly lawful, endlessly surprising. And its edge is the horizon of what we're allowed to know.